almost everything astronomers claim to know about the universe, its size, its age, its contents, its very rate of expansion, rests on the answer to one deceptively simple question: how far away is that? It is the hardest measurement in astronomy because distance uniquely cannot be read directly off the sky. A telescope records a position, a brightness, and a spectrum. The third dimension, depth, must be inferred. And it must be inferred because the light we receive from an object tells us its true luminosity only. If we already know its distance, the two are locked together by the inverse square law. The response, built over more than a century, is the cosmic distance ladder, a sequence of methods in which each rung calibrates the next, reaching from the nearest stars out to galaxies billions of light-years away. Errors accumulate as you climb, so every rung is obsessively cross-checked, and it is a disagreement of a mere 8% at the very top that has become one of the sharpest crises in modern physics. The bottom rung, and the only purely geometric one, is trigonometric parallax. As the Earth swings around the Sun, a nearby star appears to shift back and forth against the far more distant background, tracing a tiny ellipse over the course of a year. The size of that shift betrays the distance by simple triangulation, and it defines astronomy's fundamental unit. The parsec, the distance at which the radius of Earth's orbit would subtend an angle of just 1 second of arc, about 3¼ light-years. The distance in parsecs is simply 1 divided by the parallax angle in arcseconds. The method's beauty is that it assumes nothing about the star's physics. It is pure geometry, and that is why it anchors the entire ladder. Its weakness is reach. The angle shrinks with distance, so that a star 1,000 parsecs away shifts by only 1,000th of an arcsecond, a measurement far beyond the reach of any telescope on the ground. So demanding is that measurement that although Copernicus had predicted stellar parallax, none was detected for nearly 3 centuries. Its absence was once even cited as evidence against a moving Earth. The first success came only in 1838, when Friedrich Bessel measured the tiny annual wobble of the star 61 Cygni and found it to lie about 3 parsecs away, the first time the distance to any star beyond the Sun had ever been directly known. That it took so long and reached so few stars made parallax the great bottleneck in mapping the cosmos. The nearest star to the Sun, Proxima Centauri, sits about 1⅓ parsecs off, its parallax a mere 3/4 of an arcsecond. Everything else is smaller still. For most of astronomy's history, only the nearest few hundred stars could be reached this way at all. The breakthrough came from going to space. In 1989, the European Hipparcos satellite, freed from the blurring of the atmosphere, measured precise parallaxes for over 100,000 stars, the first homogeneous, all-sky catalogue of geometric distances. But the true revolution is Gaia, its successor, operating 1.5 million kilometers from Earth. Gaia has measured the positions, motions, and parallaxes of well over 1 billion stars, with a precision of tens of millionths of an arcsecond, a 1,000-fold leap over Hipparcos, pushing reliable geometric distances out to several thousand parsecs, and sweeping up huge samples of the very stars that calibrate the next rungs. Gaia is now so precise that its own tiny systematic errors dominate the budget. A minuscule offset in its parallax 0 point must be carefully modelled and removed, and this correction is one of the leading concerns at the very foot of the ladder. Between the geometric reach of parallax and the luminous reach of the great standard candles lies a set of bridging techniques that exploit stellar physics directly. The key tool is the Hertzsprung-Russell diagram, the plot of a star's luminosity against its temperature. Most stars fall along a diagonal band, the main sequence, where a star's position is fixed mainly by its mass, which turns the main sequence into a calibrated ruler. Read a star's spectrum, classify it, and you can look up its true luminosity and so infer its distance, though only to a rough 20 or 30%. Far more powerful is the same idea applied to a whole star cluster, whose members all lie at one distance. Slide the cluster's observed main sequence up or down until it overlays a template of known brightness, and the offset gives the distance at once. This method is bootstrapped from the nearest rich cluster, the Hyades, whose distance was pinned geometrically, and which in turn calibrates the ladder's crucial variable stars. Beyond the parallax horizon, distance finding turns to standard candles, objects whose true luminosity can be known from some other clue, so that comparing their true brightness to their apparent brightness yields the distance directly. The archetype is the Cepheid variable, a massive evolved supergiant that pulses in brightness over days to weeks. In 1912, Henrietta Leavitt, studying such stars in the small Magellanic Cloud made one of the pivotal discoveries in astronomy. Because all those stars lay at essentially the same distance, their apparent brightnesses could differ only by their true luminosities, and she found that the longer a Cepheid's pulsation period, the brighter it intrinsically was. This period-luminosity relation, the Leavitt law, meant that simply timing a Cepheid's pulse reveals its true luminosity, and hence its distance. It was with Cepheids that Edwin Hubble, a decade later, proved the Andromeda Nebula to be a whole galaxy far beyond the Milky Way. The Leavitt law is not mere coincidence, it has a physical root. A Cepheid is a pulsation engine, a star trapped in a narrow instability strip where a layer of partly ionized helium acts as a valve, storing and releasing heat to drive the star's rhythmic swelling and shrinking, and the period of that beat is set by the star's density, which is tied to its luminosity. Modern astronomers anchor the relation on three independent geometric footings: Gaia parallaxes of nearby Cepheids, eclipsing binary stars in the large Magellanic Cloud, and the water mazes of a galaxy whose distance is known from pure orbital geometry. Yet Cepheids carry hazards. They live in dusty, crowded regions, so dimming by dust and confusion with neighbors are persistent worries. And there was once a notorious trap, when two distinct classes of Cepheid were conflated, an error that, when Walter Baade untangled it in 1952, roughly doubled the estimated size of the universe overnight. Because such systematics can hide, astronomers prize an independent stellar candle to cross-check the Cepheids, and the most important is the tip of the red giant branch. As a low-mass star ages, its inert helium core grows until, at a sharply defined critical mass, the helium ignites in a sudden flash, an event that happens at almost exactly the same core mass, and therefore at almost exactly the same luminosity, every time. Observationally, this shows up as a crisp cutoff at the bright end of the red giants in a galaxy, a natural standard candle. Its great virtue is that old red giants populate the clean, dust-poor, uncrowded outer halos of galaxies, precisely where the Cepheids' troubles vanish. An entire rival measurement of the expansion rate has been built on this method, and it lands slightly lower than the Cepheid-based value. Because the two ladders share the same geometric anchors but rest on utterly different stellar physics, their comparison is one of the field's sharpest tests for hidden error. The red giant tip is only one of a growing family of stellar candles deployed precisely so that no single method's failure can masquerade as a discovery. A newer one uses a particular kind of carbon-rich giant star whose brightness clusters tightly around a stable value, offering a check independent of both the Cepheids and the red giant tip. Older, fainter pulsating stars called Lyrae serve as candles within our own galaxy's halo and its globular clusters where Cepheids are absent, and for distant elliptical galaxies, too far for any single star to be resolved, astronomers gauge distance from the very graininess of the galaxy's light, the statistical speckle of its unresolved stars, which smooths away with distance in a measurable way. Each occupies a slightly different niche of stellar population and distance range, and each is vulnerable to a different set of errors. The modern strategy is deliberately to overdetermine the ladder, measuring the same distances by as many independent routes as possible so that where they agree the result can be trusted, and where they disagree the discrepancy points straight at the hidden flaw. Not all distance indicators are single stars. Some exploit whole galaxies. The most famous is the Tully-Fisher relation, discovered in 1977. The luminosity of a spiral galaxy is tightly tied to how fast it rotates, a speed read straight from the Doppler broadening of its hydrogen radio line. The logic is that a galaxy's rotation reflects the mass of its great dark matter halo, which in turn scales with its luminosity, so a velocity which is distance-independent predicts a luminosity which reveals the distance. Its cousin for elliptical galaxies links their luminosity to the spread of their stars' random motions. These relations reach vast numbers of ordinary galaxies far beyond the range of rarer candles, and they are indispensable for mapping the cosmic flows of matter. Their weakness is scatter. Good to only 15 or 20% per galaxy, they are statistical tools, averaged over many rather than precision rulers for any single one. Yet their reach is their strength, for they sample thousands of ordinary galaxies, and so map the gentle tug of gravity that pulls galaxies away from the pure expansion. The peculiar velocities that must be subtracted before a clean expansion rate can be read from the nearby universe, and the very tightness of the Tully-Fisher relation carries a deeper puzzle. In its purest form, linking a galaxy's total ordinary matter to the fourth power of its rotation speed, it is a central and still debated clue in the long argument between dark matter and modified theories of gravity. The rung that finally carries the ladder into the deep, smooth expansion of the universe is the Type Ia supernova. These are the thermonuclear detonations of white dwarfs, the dense embers of dead stars when, by drawing matter from a companion, they approach a critical ceiling, the Chandrasekhar mass of about 1.25 times the Sun, beyond which they can no longer hold themselves up. Because that trigger mass is nearly universal, the explosion's peak brightness is nearly uniform, and for a few weeks a single such supernova can outshine its entire host galaxy of 100 billion stars, blazing bright enough to be seen across billions of light-years. Here at last is a candle brilliant enough to reach the realm where the universe's expansion swamps all local motion. Type Ia supernova are not perfectly identical, but they are standardizable. In the 1990s it emerged that the brighter ones fade more slowly, a regularity that, together with a correction for dust, tightens their scatter to a remarkable 5 or 7%, making them the most precise single-object distance indicators known. Their absolute brightness is calibrated by the crucial handoff of the whole ladder, catching a Type Ia supernova in a galaxy near enough that Cepheids or red giant tips fix its distance directly, of which only a few dozen exist. Those calibrate a supernova set the true brightness of the candle. The same standardized supernova, seen far out in the expanding flow, then set the slope of velocity against distance. It was these very explosions that, in 1998, revealed the universe's expansion to be accelerating, driven by a mysterious dark energy, a discovery that won the Nobel Prize and remade cosmology. The top of the ladder converts all these distances into the universe's expansion rate. In 1927, Georges Lemaitre derived an expanding universe from Einstein's equations and predicted that galaxies should recede at speeds proportional to their distance. 2 years later, Edwin Hubble demonstrated the law from the data, and it now bears both their names. The constant of proportionality, the Hubble constant, is the present rate of cosmic expansion, and it is one of the most consequential numbers in all of science. It fixes the scale of the observable universe, and its inverse gives a rough measure of the time since the Big Bang, some 14 billion years. Every rung of the ladder we have climbed exists ultimately to pin down this single quantity, and to do so, the recession of distant galaxies, read from the redshift of their light, must be divided by their hard-won distances. The flagship modern effort is the SH0ES team, led by Adam Rees, and its measurement is a marvel of accumulated precision. It rests on 3 independent geometric anchors, the parallaxes of Milky Way Cepheids, eclipsing binary stars in the Large Magellanic Cloud, and the water mazes of a nearby galaxy whose distance owes nothing to any candle, which together calibrate the Cepheids. The Cepheids, found in the host galaxies of 3 dozen Type Ia supernova, calibrate those supernova, and the supernova, seen far out in the smooth flow, fix the expansion rate at a value near 73 km per second per megaparsec, with an uncertainty of barely 1%. When critics suggested that the crowding of Cepheids in distant galaxies might be biasing the result, the team turned the sharper infrared eyes of the Webb telescope on the very same stars, and found the local value unmoved, holding firm near 73. That number, near 73, is the heart of the deepest controversy in cosmology, because a completely different method gives a stubbornly different answer. The expansion rate can also be inferred, not by climbing a ladder at all, but from the infant universe. The Planck satellite's exquisite map of the cosmic microwave background, fitted to the standard 6-parameter model of cosmology, predicts a present expansion rate of about 67.5. The two figures differ by roughly 8%, and because both are now so precise, the gap between them amounts to about 5 standard deviations, the level conventionally regarded as a discovery if it reflects something real. This is the Hubble tension, and it will not go away. It must be flagged clearly as an open problem, not a settled fact, and its possible resolutions fall into 3 broad camps. Perhaps there is a subtle error somewhere, in the local ladder, in the Cepheids' dust or crowding, in the parallax offsets, in the supernova calibration. Perhaps instead the early universe analysis is missing something, or perhaps neither, is wrong, and the answer is new physics. Since the microwave background value depends on a cosmological model, altering the early universe, for instance with a brief burst of early dark energy that shrinks the sound horizon ruler imprinted on the sky, could raise the inferred rate into agreement. None of these fixes yet works without creating fresh problems elsewhere. The way to break the deadlock is with methods that avoid both the Cepheid ladder and the microwave background entirely, and several now exist. The gravitational bending of light by a foreground galaxy, timed by the flickering of a distant quasar behind it, gives a direct distance. So do gravitational wave, standard sirens, the ripples from merging neutron stars, which encode their distance in the very shape of the wave, read off without any candle at all. The first such siren gave an expansion rate consistent with either camp, but far too imprecise to settle the matter, and the red giant tip ladder, built to sidestep the Cepheids, consistently lands a little lower than the supernova value. As yet, none has delivered the decisive verdict, but each is an independent line of attack on a problem that has resisted a decade of scrutiny. A fourth approach turns the whole ladder upside down. Instead of building up from nearby stars, one can measure distances from the top down, using a standard ruler rather than a standard candle, the Baryan acoustic oscillation scale, a fixed length frozen into the distribution of matter by sound waves in the early universe. Vast galaxy surveys map that ruler across billions of light-years, and the Daisy survey, charting millions of galaxies and quasars, yields an expansion rate near 68.5, close to the microwave background value, and well below the local one. So the inverse ladder, too, sharpens rather than dissolves the tension, and it has reopened a further question of whether dark energy is truly constant or slowly evolving. It is worth being scrupulous about what is settled here and what is not, for the distinction is the whole point. Settled beyond serious doubt are the architecture of the ladder itself, parallax to candles to supernova to the expanding flow, the geometry of parallax, the empirical laws of Leavitt, of the supernova, of Tully and Fisher, the reality of the cosmic expansion, and the existence of dark energy. Genuinely open is the exact value of the expansion rate, and whether the local and early universe measurements can be reconciled with the standard model at all. And frankly speculative, to be flagged as such, are the specific new physics mechanisms proposed to relieve the tension, none of which yet commands consensus. The cosmic distance ladder is therefore two things at once. It is one of the great triumphs of observational science, a chain of reasoning refined across a century from Leavitt's photographic plates to Gaia's micro-arcsecond precision and the infrared eyes of the Webb telescope, that measures the size and age of the entire universe to within a few %, and it is the stage on which that science's sharpest present crisis is being played out. The very precision that is the ladder's crowning achievement is what makes its disagreement with the early universe impossible to wave away. Within the coming decade, with the flood of supernova from new all-sky surveys, further Gaia data, the Roman Space Telescope, and a growing catalogue of gravitational wave sirens, the two values will either be driven into agreement, quietly resolving the tension as some overlooked systematic, or they will hold apart and force upon us a revision of fundamental physics. Either way, the humble question with which we began, how far away is that, remains the thread from which the whole fabric of cosmology hangs.